Hey, this is Joydeep. Can you hear me?
Yes, Jyoti, we can. If you like to introduce yourself over the chat, that'd be great.
Okay, sure.
Yeah.
So in about a couple of minutes, we'll get going by intro, and then Louis will start with his talk. So if there are any folks who are here for the first time, please make sure to follow our LinkedIn page, join the group, and become a member so you can get all the updates. Usually after the events, we send out a packet with the summary of the event, any links, any special offers, and clips from the session. So you will get all of that if you're plugged in and connected with us. Oh wow, Louis, you have many fans in the audience.
Oh, that's nice.
Yeah,
Thank you.
small world.
To see everybody.
Yeah.
I see a lot of people from Austin. I used to go to Austin a lot for work back when I was at Austin. Beautiful place.
I see. I see.
Such a charming place. Yeah.
Mm.
I went in like June, July, so it was hot.
Oh, so next time you go to Austin, you have to stop by Dallas too.
Absolutely. I'll
Yeah.
just do the
Mhm.
yeah, I wanted to go to the Grand Prix and I never made it happen. But yeah.
Mm. All right.
I think we can get
Oh,
started.
yeah,
Baba.
let's get started. So welcome everyone, Dallas AI. We're very excited to have Louis Serrano here with us. So Louis and I met when we were working for the same company, Zapata Computing, a couple of years ago, and I immediately was, so impressed by the amazing work that he was doing there. And then I discovered that, he has a lot of interesting things that he's going on. So let me start with first saying that, he has an amazing YouTube channel, Serrano Academy, and you will get the links and we will post it on our social media sites as well, but it's essentially Serrano Academy. So that you can benefit from the really intuitive videos that he produces. And by the way, those videos they look simple and intuitive, but they take a lot of time to do it. He's also the author of a book called Grokking Machine Learning, published by Manning. And in the chat, I placed a discount code for 40% off there. It's a highly recommended book. You will learn a lot about the fundamentals of machine learning and some of the advanced topics in there. Third thing, he is the instructor for a very interesting recent course at Coursera with Andrew Ng on the math for machine learning and AI. And I'll ask Louis to just, tell us a little bit about that after my brief intro. But I'm not done yet because he has one more thing that just happened today. That's based on, he's currently at Cohere.ai, a company that helps organizations to use large language models. And it's actually partly funded by Jeffrey Hinton, the godfather of AI. So I think I'll pause here and I'll let Luis correct any of my mistakes or add something about the LLM University that just happened and take it from there.
No, that was wonderful. Thank you. Thank you so much for that kind introduction, Babar.
Thank you.
We used to work together at Zapata Computing and did some wonderful things. I always really enjoyed talking to Babar. So when he invited me to talk, I said, of course. This is a really, really nice group. So thank you. And thanks, Amber, as well for the invitation, and to everybody that says hi in the on the chat. Very excited. So yeah, let me no, everything you said was very accurate. So let me actually share my screen and show some links. So desktop 2 is the one that I want to show you. So yeah, this is really fresh. Actually, today, just today, we launched this thing called LLM University. The link is very easy. I'm going to put it in the, it's just literally llm.university, large language models.university. And it has a bunch of stuff. You know, we talk about what are large language models. What I'll tell you today, a lot of it is in LLM, is basically module 1. And then we have a bunch of stuff on, these are my 2 fellows, which are wonderful instructors. They both have books and YouTube channel with a lot of followers. And then we talk about, you know, code. We give a bunch of labs, Google Colabs, and then there's the cool one, which is just generation. What we've been hearing a lot lately is in the Cohere models. It talks about prompt engineering, which is something that's very hot right now. Yeah, so take a look at it, llm.university. This is the course that Babar was kindly talking about, mathematics for machine learning and data science specialization. It's in Coursera, 3 courses. First one is linear algebra, second one is calculus, third is probability statistics. They're all geared towards machine learning. There's nothing we put there that's not guided towards machine learning. So it's just basically guided to take you to the next step. Then there's this over here, Serrano.academy. That's just my page where I have all the videos. I have blog posts, a bunch of stuff on classical, quantum computing, machine learning, everything. This is the book over here that Babar will kindly share a discount code that I'm sharing with the audience. Here's the YouTube channel. Not supposed to be playing video, but yeah, this is the YouTube channel. So a bunch of videos on basically all of machine learning. And my style is I like to understand things in a very basic way. So I put everything in cartoon mode. I barely ever use a formula because I try to understand everything with the sort of in a graphical way with examples like I'll show you today. So yeah, so thank you, Babar. And then you know, at the end I'll give you a little demo of the Cohere models, the playground. So yes, I'm going to share my screen, but before that, I'm going to get the chat. And let's see, if I share my screen, I see the chat. So this will be wonderful because I'll be able to see any questions in real time. I'll be able to answer them. This is your time, so you know, ask me anything you want. If you want to go on a tangent, we can go on tangents. This is really, it's really your time. Sorry, I'm taking my time because I'm putting my windows all together. So I do see, okay, I do see the chat. All right, just figure this out. So yeah, this is the, as I said, the LLM University link. Okay, so today I'm going to tell you about these wonderful things called transformers, which you may have heard them, you know, just all over the place. ChatGPT, the transformer model, they came out recently, and they really made a huge step in natural language processing. My mind was blown when I started seeing how these models talk to us like a human. They really make one huge step. And what really happened is, you know, obviously more data, bigger computers, and a few key aspects in the architecture of a transformer, attention models, and a few other, which I'll tell you today. So transformers is what we are going to talk, and what they do, pretty much, they generate text. Now, generating text is nothing new. I'm sure you've seen. I'm sure you've used your phone at some point and texted and seen the what's the word? The recommendations that you get for the words, right? Like I use in my text messages, you go, hello, how are, and then you get a recommendation called your or your things or something. And yes, I see attention is all you need. Somebody put in the chat. That's the paper that started it all. It's actually one of the authors is the CEO of the company I work with. Go here. So anyway, so this is nothing new, right? So transformers really just generate text. The question is how, and let's just start the easiest possible thing. The hello world of generating text. What's the easiest way to generate text? If I say hello, how are, and let's just say you're starting computer science, starting programmer today, and you want to write a one line of code that will help me find the next word here, what would you do? I wonder if anybody wants to suggest something very simple that will help put some word there that works. Yes, the answer would be you. I would say, as JD suggested. But how would you code it? Like, what would you do to make the computer put the next word there? And hopefully it would be you. It could be elephant. Maybe it messes up, but let's hope that it puts a good one. What would you do to put a decent word there? And let's just assume that you have a lot of data, so you have a lot of conversations, and you can search. So based on the last 3 words of the sequence, you would see the problem. Yeah, exactly. Good job. That would be at what's called an n-gram. So I'm going to use an even simpler one. I'm going to look one word, right? So I'm going to pick the word R and just put it, look at my huge data set and find all the times the word R appears, and then look at what word comes next. So let's just say that the most common one was happy. So hello, how are, happy. Okay, that's not ideal, but at least it, may work occasionally, right? If we want to get better, we can do exactly what Joydeep suggested, right? Like we can do 3 words, trigrams, right? I look in my huge data set and see what's the most common word that happens after hello, how are, and let's just say it's things. So we go hello, how are things, right? Now, I don't know if you've tried this. If you start typing the middle button, the suggested word on the text, you get some crazy stuff. For example, this hello, how are you feeling this week, and your kind wishes for a wonderful weekend with your kindness and happiness for your family, love, and your kind. I kept doing that, and I get that, and you get insane text. However, they look like they make sense, a few words at a time, right? Like happiness for your etc., etc. So they do capture like some kind of local context, but nothing larger, right? What transformers do? This, except they carry the context. So here's something. Let's do something more extreme, right? Yeah. So I see as suggestions here. Yeah, correct. If you see hello, how are, then put you. Yeah, we do trigrams, right? So let's say we want to do a much better job than with 3 words. So what about 10 words, right? Like if I say, hello, today I would like to inform you that, and then I look in my data set and it says, hello, today I'd like to inform you that the, so the word is there. What is a possible drawback of this method, a 10 gram? Who can tell me what could go wrong here? Any ideas? You can also talk if you want. If anyone just wants to put their mic on and, what do we think? Very low probabilities for any option. Yes. It could happen that perhaps I give something that's never, that doesn't appear in the data set. I could say today, yeah, I was walking. Yes, exactly. Too specific. I hear good, correct answers. The other day I was walking and 5 unicorns said, maybe that sentence just never appears in the data set. So the data set has nothing to do, nothing to say there. So we need something more advanced. We need something that's not so deterministic, and that's actually able to completely guess something if you give it sentences that never appear, right? Something that a sentence that never appears still kind of guesses what to do. So we need something called, well, we're going to get to neural networks eventually. But how many people here have seen sentiment analysis? Yeah, somebody says yes. Should NLP be used? That's exactly what we're doing. We're going through NLP. This is a 0 to 100 of NLP. So sentiment sentiment analysis. I see some thumbs up for people who have seen sentiment analysis. Sentiment analysis is pretty much the quintessential basic application of NLP. One of the first things that was done in machine learning with NLP, and what it really does is it checks if a word is happy, or if a sentence is happy, or if a sentence is sad. So for example, I'm very happy is a happy sentence. Today was awful is a sad sentence. And what it does is it takes a data set of existing sentences that are labeled happy and sad. And from there, it infers information to find if a new sentence is happy or sad. So here's a question for you. Let's say that your boss comes in and says, "Hey, write me something quick." Just like they said, write me something quick a minute ago about finding the next word. They said, find me some quick and dirty algorithm that will build a sentiment analysis model, so that when I give it a sentence, it tells me if it's happy or sad. And don't worry, this doesn't need to work 100% of the time. If it works 60 or 70% of the time, I'm good. I just need something quick. Any ideas? Who wants to tell me in the chat any idea? How would you tokenize and look for happy and sad words? Sounds good. Yeah, we got experts in the crowd. It's good. Yes, we'll talk about tokenize. But let's look for happy and sad words. So for example, happy, let's say I'm gonna assign points. So positive points for a happy word, negative points for a sad word, and a super happy word has a lot of points, and a super sad word has a super low scores. Oh, I see Grammarly. Actually, Grammarly may work, right? Like, does that have sentiment analysis? Cool. Somebody says a simple grep and look for words. Single neuron, a GPT model is detected non-activate for sentiment determination. Yep, a single neuron. We're gonna get there. Yep. I like that the next topics are being predicted by the crowd. So thank you. Yes, Alan, we need to recognize words like not. We'll get there. But here's a question. Let's say that we want to come up with these scores, and let's all of us, right? We're like 50 something people. Let's all come up with a bunch of scores that are positive for words that we know that are happy, and negative for words that are not happy. So one thing we could do is just kind of split the dictionary among all of us and start assigning points to words, right? But that's too much work. And also that requires us to know the language. We could do this in a language that perhaps we don't talk, we don't speak, if we have the right data set, right? So any ideas on how to do this automatically? And we have a data set, right? Yep, we have labeled data. Marshall says the data is labeled because it says each sentence has a label happy or sad. So for example, the sentence, "What a happy day," has a label happy. How would we do to automatically be able to assign scores? Fernando says embeddings. We're gonna get to embeddings. Yeah, you guys are predicting all the topics that happened today. Clustering may work, as Benjamin suggests. Yeah, I have a different one than clustering, but clustering may work. But yeah, kind of. So an idea would be kind of imagine something iterative, right? Like if I see a happy sentence, I add a little bit. I have some I start with random scores or with zeros or whatever I want. And when I see a happy sentence, I add a little bit to all the scores. And when I see a sad sentence, I subtract a little bit to all the scores. Marshall suggests to use ChatGPT, but the idea is that we're building ChatGPT one step at a time. But yeah, ChatGPT would be a good one for that. But we're going super basic, right? So if I take all the sentences and I go through every sentence, and for a happy sentence, I add a little bit to the scores of the words. And for a sad sentence, I subtract a little bit to the scores of the words, right? And eventually I would end up with pretty good scores for happy words and bad scores and negative scores for sad words, right? That's kind of what training an algorithm is, like training a model is, right? Very, very slowly. And that plus a little bit is what training a model means, right? I go through all my data set, and every time I see a sentence, I adjust the models, I adjust the weights a little better so that it does better for that sentence. So eventually we can end up with pretty good points, and I can just add them and have, if I get a positive score, I have a happy sentence. I say the sentence is happy. And if I have a negative score, I say the sentence is sad, right? And at the end, I end up with, you know, all the words from the first one to the last one, and each one has some scores. Neutral words have a score close to 0, I expect. And happy words, positive scores, and sad words, negative scores. And that, as somebody said earlier, is a neuron, right? It's a perceptron. That's the basic unit of a neural network, right? What I do is I'm going to put all the words in the red dots, and for each of the scores, I'm going to put them in the edge that connects to some blue dot on the right. And then when I have a sentence, for example, I am happy, what I do is I put ones in the red dots where the words are, and I multiply each red dot by the edge. So I only add the ones that are corresponding to the words in the sentence. And I get, for example, here 3.2 minus 0.2 plus, oh, I think I messed up. There's a 0.2 that should be a 0.1. Anyway, the fact is I get 3.1, and that's positive. So the model says that the sentence "I am happy" is a happy sentence. Sounds good. What's a possible problem, right? Somebody mentioned something here that the word "no," for example, could be an issue, right? Language is a lot more complex than this, right? I'm sure you can imagine that assigning a score to every word, exactly. Assigning a score to every word does not figure out the English language. There's sarcasm, there's ways to organize the words. I could reorganize the words in a sentence and change the meaning completely. So it's really more, you know, there's a lot more to the English language and to any language than just assigning scores to words. But we can get a little further. So here's a problem: that language is a lot more complex than that. And let's look at what a neural network is. So some of you may know neural networks. If you don't, we're introducing them. If you do, this may show them to you in a different light. But the idea is that, you know, we've established, so this would be what's called a neuron, right? A neuron is supposed to emulate the neurons. It's not nowhere close to how they operate, but they emulates it because, you know, signals come from one side, gets processed here in the blue dot, and then some output comes out, right? A 1 if it's happy and a 0 if it's sad. And so that's sort of mimics what a neuron would do, where something comes in and something comes out, like a synapse or something. I don't know about the brain. So, but that's called a perceptron. It's a basic unit of the neural network, right? And the output would be, you know, 1s and 0s come in, and the output is 1 if the neuron thinks the sentence is happy, and 0 if it thinks it's sad. However, here's a problem that we're gonna come up with a, you know, slightly rough solution. Let's say that happiness and sadness is a complex concept, right? It's not something that can be easily inferred by just adding scores to words. But maybe there are other concepts that are simpler and that are easier to model by just adding scores, by just assigning scores to words. Let's say, just bear with me here. It takes a lot of imagination, but let's say that there are simpler concepts. For example, if you have free time or not, let's say that that's easy to model by adding, by scoring sentences. Let's say that if you talk about your family, and if you talk about being hungry, maybe those are simpler concepts that you can do better that you can guess in a better way by assigning scores to words. And let's say that out of these concepts, you can define happiness. Let's say that if I have free time and I have family and I'm not hungry, I'm happy. That's why there's a -2 there, right? I'm not hungry, and a 3 for family and a 2 for free time. Let's just pretend. Let's pretend that that's the case, right? And so we have what's called a neural network. And these will do a little bit better because they get to capture the complexities of the language a little more. And you can go nuts, right? You can have a really deep neural network where the first layer is just neurons that capture very simple concepts. They get to a next layer where the concepts are a little more complicated, and that gets to a next one and a next one. And then the last layer is a more abstract concept, and then the last one is happy, sad. And if you do this, it works better. And you can do something like this and train a neural network just like we train the individual perceptron. And that does well. You can actually get like 80% accuracy with this in normal sentences. I see some questions as, but subsequent connected neurons will have 0, 1 as the input. Actually, I kind of lied when I said 0, 1 at the input. The input could be anything from 0 to 1. So it could be a continuous, anything. It could be 0.5 if the model's not sure, 0.8 if it's happy, 0.2 if it doesn't think it's happy. And so that means they're easier to train using calculus, like taking derivatives. But the idea is that you let the computer run. You let the computer train this by going through all the data and always trying to change the weights to make sure to improve on each of the sentences. But obviously the computer doesn't know these concepts that we have over here. The computer just says, random stuff for the brain cells, for the neurons. But somehow the model figures out some concepts to put on on each of the layers. And at the end, the point is that it gets trained to tell if a sentence is happy or sad. So this is a neural network used for sentiment analysis. Who can help me with applications? What do you think are good applications of sentiment analysis? And while I think about it, I look at some
like customer service.
Customer
Or
service, good
brand.
job.
Yeah.
You're guessing, yeah. Reviews, yes. Customer service contact center, yes. A chat with a representative, for example, reviews of a movie, reviews of products. You can also have, for example, let's say
Marketing, branding, right?
say that again, sorry.
Marketing, branding, right?
Marketing, branding, anything you want to see how people are happy with if people are happy or sad with a particular product that you're selling, et cetera, et cetera. I see social media post filtering, patient care, of course, greeting card construction, lots of stuff. Yeah, this is very useful. And let me go
elections, right?
Yeah, elections.
Yeah,
Exactly. Twitter data, anything like that. Now, here's the thing. There's nothing special about happy, sad. That's just something I put on the data set. But I can also do A or B, right? I can give it emails and I can say spam or no spam and do exactly the same thing we did with happy, sad. I'm just training the model to understand what words are spammy and what words are not spammy, right? So spam detection. And nothing says that I have to have only 2 answers. I could have more, right? I could have, for example, when you go on Gmail and it classifies your email into 4 things, it goes, let's say, personal, important forums, social promotions. You can still do that, right? That's sentiment analysis. It's just the sentiment is not happy, sad, but it's personal, email, promotion, forum, social, right? Same thing. And in particular, here's a question. Why am I talking about sentiment analysis when we were talking initially about adding the next word to a sentence, right? I see more suggestions, security, virus detection. Yeah, pretty good. Why am I talking about sentiment analysis when we were first talking about adding the next word in a sentence? And the reason is because it's the same thing, except that I don't have 2 outputs or 4 outputs. I actually have as many as words, right? My output, if I have, I don't know, 10,000 words, my output can be 10,000 words. Exactly. It says sentiment determines the next word. I can make it determine the next word. So here's, for example, if I have one neural network with 3 outputs, it tells me if my email is personal, work, or email. Or invitations. I just put more neurons in the last layer. And if I put as many neurons in the last layer as I have inputs, then this is going to return one, is going to tell me one word in the dictionary. So if I start with how are, then the neural network will get trained to say you. Okay, so a neural network can be used to predict the next word in a sentence, right? Okay, so that's like 10 years ago technology. That's a while ago. That's what the phone uses to guess the next word. So it's not that great. And we can enhance it. We can make these architectures more complex, things called convolutional neural networks, recurrent neural networks that just act. They're better at keeping the sequencing of the language, and things kind of worked until a few years ago with just neural networks, but they didn't have the level that the transformer models have now. So the question is how to transformer models work. I'm going to tell you what's so special about transformer models that make them do well. But it's really just this with it's a neural network with a lot of extra padding on the sides. Sorry, my clicker stopped working. Okay, there. But at the end of the day, it does nothing more than guess the next word. So for example, if I start with hello, how, the transformer says are. And how does it create that wonderful pieces of text that you see? Word by word. So you say, write a story, and it goes, okay, well, the next word after write a story is normally once. So, okay. Then how does it take the next word? It goes, write a story once. That's the new input. And you say upon. And then you enter, write a story once upon, and it goes, well, probably write a story once upon and then the next one is time, and that's how it goes, right? So no different. But as we saw before, a neural network is able to say the next word. Sometimes it does well, sometimes it doesn't do well, but the fact is it tries. And a transformer does this really well. So how I imagine them, a neural network would be like a truck, and a transformer is like a truck with a lot of stuff attached to it that makes it work better, right? So an actual transformer. And the architecture of a neural network, as you saw, is a bunch of layers, right? Feed forward layers, one, then passes to the next one, passes to the next one, passes to the next one. And in a transformer, the architecture is this. So as you can see, the blue stuff is still the same, right? The blue stuff is still the same over here, but all the pink stuff has been added on the side to make it perform better. In particular, if you see the word attention, that's really what did it, the attention model. So here it is. And so I'm gonna go through all these architecture. In the meantime, since there's a change, let me see if there's any questions in the chat. So Neil says, do the same rules apply for complex documents such as legal, tax, language? Yeah, the same rules apply, because at the end of the day, you're just associating words with whatever sentiment you have. So actually, it may be harder for humans, but for computers, it's pretty much the same. Steve says, can I train models from scratch with all Shakespeare books in order to generate stories similar to his work as the way predicting the next word? Absolutely, and that's what they do. You can throw in all the Shakespeare, and then it just generates Shakespeare-looking stuff. That's what transformers do really well. So anyway, so let's start with tokenization, right? So tokenization, it's the simplest step. It just has a bunch of tokens, pre-selected tokens, one for each word, one for each punctuation sign, etc., and it turns it into pre-existing tokens. This is just a pre-processing step. Then comes embeddings, which somebody asked before, right? Embeddings are, I would say, the most important part of natural language processing, of large language models. It is really where the rubber meets the road. Why is it? Because humans, we're very good at words, and computers are very good at numbers. But what's the translation? So the translation is the bridge between them, and the bridge between them is an embedding. So embeddings are really where computers talk, basically, where they turn words into into numbers because they're very good with numbers and we're very good with words, but the translation needs to happen. And the better embeddings are, the better models are. If tomorrow somebody comes up with an embedding that's 10 times better than all the previous embeddings, then I guarantee you the models are going to be 10 times better than the previous models. A good embedding is just makes everything better. And how do they work? Well, here's a quiz for you. Okay. Embeddings assign numbers, assign words to numbers. And yes, Srisham, I will be talking about word2vec pretty soon. But let's think of a very simple embedding. This embedding assigns the words to two numbers, the street and the avenue, right? The horizontal coordinate and the vertical coordinate. So for example, basketball is 1-6 because it's a 1 horizontal and a 6 vertical. And the quiz that I have for you is, where would you put the word apple in this embedding? So would you put it in A, would you put it in B, or would you put it in C? I'll take answers in the chat. I see C, C, C. Yep, very good, everybody. Good job. You all pass with flying colors because I would put it in C. And why would I put in C? You can imagine the reason is because the fruits are close by. So in an embedding, close, similar words have similar numbers and different words have different numbers. Okay, exactly, Miles, the similarity of meaning. So I would put it in 5-5 or somewhere around there. That's a very important thing of embeddings. And there's another one. Here's another quiz. Where would you put the word cow? So I have puppy, dog, and calf. A, you put it at B, or would you put it at C? And while you think about it, I'm going to answer Arvind's question. How did we determine the positions of those objects? We're going to get there soon. I'm going to show you how to build an embedding. Okay. Srisha says, but it can refer to product also. Normally, no, I think we're just mostly adding. I'm not sure what you mean by product.
Like Apple laptops, Apple company.
Oh, Apple. No, I meant the fruit. Yeah. Actually, you're getting to somewhere that we're going to see soon, which is attention, because attention is what helps you tell if I'm talking about an Apple fruit or an Apple computer or an iPhone or something. So yes, things are ambiguous. I see some A, I see some B, I see some C, I see more C's. So yes, the answer is C. I would put cow in C. And the answer is that, well, I'm going to give you a non-answer, but it's sort of an idea, which is analogies, right? If you think about it, a puppy is to a dog like a calf is to a cow is the same as these two horizontal arrows, right? And if I say a puppy is to a calf like a dog is to a cow, that's this vertical arrow. So analogies are captured in embeddings. But more than that, really what happens is that every axis kind of means something, right? If I look at the horizontal axis, that's kind of the age, right? Like the age increases as I move to the right. If I had a really old dog, it would be in the very right, right? And this one captures the size. So I have a dog and then a cow. If I had a whale, it'd be way up, right? If I had an ant, it would be way on the bottom. Because every axis actually means something. So here we have that the first coordinate means age and the second one means size. And I could have more coordinates, right? If I had more coordinates, then I don't live in the plane anymore. I now live in 3-dimensional space, right? Because I have 3 coordinates. And yes, as Joydeep says, yes, this is definitely vector math, right? I'm adding vectors and do parallelogram rule and stuff like that. And I would just have words flying all over the place, and similar words go to similar points, close by points, and each axis actually means something. But of course, embeddings are not going to be length 2 or length 3. They're going to be length a lot. An embedding that we use in our models at Cohere, 4,096 values for each word. So they mean things, right? For example, they could mean size, they could mean color, etc. Or they could just mean random things that the model kind of figured out. And maybe we can interpret it, maybe we cannot interpret it, doesn't matter. The fact is each vector of like 4,096 now knows a lot about the words. And Fernando's talking about cosine similarity. Yes, exactly. Cosine similarity is a way to tell if two things are close in the embedding or not. So it would be like a high similarity for similar words and low for others. And you can also do this with sentences, right? You can have entire sentences mapped to long vectors. And so here's us, and I was playing with the embedding, the coherent embedding that I will show you in a bit. And I brought it down to 10 dimensions. So it didn't do 4096, but I crunched it down to 10. If you've heard of something called PCA, that's what I used. And if you see, there's a lot of sentences that are similar. For example, show me a list of ground transportation at Boston Airport. Show me Boston ground transportation and what ground transportation is available in Boston. And as you can see, the numbers are very similar. I shaded, instead of adding the number, I just added shades. But you can see that they're very similar vectors, right? Because the embedding knows that even if you give it completely different words, the meaning of the sentence is captured. So this is very useful. And then another experiment I was doing, I just put a bunch of simple sentences, and the ones that say hello are this ones, the ones that talk about the dog are this ones, and the ones that talk about soccer are over here. And even if you have different words, the computer still catches that the meaning with the embedding, right? There's also a multilingual one. We have a multilingual embedding that you can test in the playground that I'll show you in a bit. And it actually sends similar sentences in different languages, over 110 languages, to similar points. So this one's talk about bears, this one over here talks about soccer and the World Cup, and this one's talk about an apple, and this one's about the sky. So so this works in different languages. So it's very, very useful. And now to get to the question that was asked a minute ago, which is how do you build embeddings? So I want to ask you, how would you build an embedding? Because they seem very useful, but they also don't seem obvious to build, right? How would you assign numbers to every word in a way that makes sense? And while you think about it, I'm going to check a question here. Is there a relationship between embedding of the words and embedding of the whole sentences? Can one be calculated from the other? That's a great question, Fernando. I would just normally calculate them separately, but if you have an embedding for sentences, it works for words too, right? Because you can just plug in a word instead of the whole sentence, and it kind of catches it. So you can even do like paragraphs and everything. So she says embedding is learned. She says encoder decoder model, training data. Yep. Yeah, the idea is to train it, right? Like, let's say we're starting from scratch, like we don't have any technology. We're trying to build we're in a deserted island and we're trying to build an embedding. We have a basic, we can do operations. How do we do it? Marshall says sentence similarity requires positional encoding. No, that's a different thing. But we will use positional encoding for transformers. Yeah, good questions. A lot of good questions. I'm going to show you a slightly messed up way of building an embedding. The idea is that we want to assign to each word a bunch of numbers. And we want that similar words get similar numbers, right? So bear with me. Bear with me, I'm going to let the imagination wild. Imagine that we have something to measure brain activity. Okay, so you put a bunch of sensors in my brain, and these sensors make some numbers appear in the screen based on some brain activity. And there's like, I don't know, 10 numbers in the screen. And when you show me an apple, then my brain reacts in some way, and the screen shows a bunch of numbers. And if you show me a pear, then another set of numbers appear. So similar numbers appear. And if you show me a truck, then different numbers appear because I have a different reaction to a truck than to an apple or a pear. So that creates an embedding, right? That kind of does it. It's a twisted way to think of an embedding, but that kind of creates an embedding, right? So the question is, can we do that, but with a computer? And the answer is, well, what do we have? That's kind of like a brain? Well, we have a neural network, right? Can we do that experiment on a neural network? Well, if we have the neural network that guesses a next word, then all you have to do is plug in a word and maybe look at that last layer. Why do we look at the last layer? Because as we established, that last layer kind of understands the text pretty well, has like some high level descriptions about the text. And so if you put in the word apple and look at what numbers come out of that green layer, that's an embedding. That's 3 numbers, right? Or it could be 10, it could be 100. But the fact is, whatever numbers come out of there are going to be similar than the numbers that come out if you put a pear, right? And different than the ones I put if I put a truck. So that's a way to create embeddings. You look at the last layer of a neural network that is trained on the words, and that creates a pretty good embedding. Is that clear? Sort of. It's important that sort of makes sense, right? So that's word2vec. Somebody asked, what's word2vec? That's word2vec. Look at the last layer of a neural network. I can explain that again, Cesar Vin. Sure. Imagine that in this neural network, right? You put you make it guess the next word, and that neural network that kind of knows a lot about the word. So if I put in, for example, the word apple, then it goes, layer, and each layer has a bunch of numbers. And you would imagine that the numbers, if the neural network is well trained, the numbers that come out if I put an apple are similar to the ones if I put a pear, and different than the ones if I put a kangaroo, right? And so the numbers that come out of the last layer are the ones that I pick for my embedding, right? Clint has a pretty good question. How did someone figure this out? I have no idea how they figured out word2vec, but it's kind of cool, right? I mean, I think they started debugging neural networks. They started looking at neural networks not as a black box, and they said, what could we do with this, right?
Hello, can you hear me?
Absolutely, yes. You want to ask the question?
Yeah. So when you say that layer upon layer, if it's trained, we're getting a number. So this vector or this series of numbers, this is going to be the second to last layer in the neural network, correct? Because the
Yes.
last layer would just be like the actual output or result. So
Exactly.
the layer right before that. Okay, thank you.
I throw away the result and I just look at the previous layer. I could look at any layer, but the last layer is the more high level one, the one that knows the most, right? So I take that one, but I could take the second one or fourth one. It's just not going to be that good. But the last one is the second last one is the best one. Okay. Fernando says, what would the training data be? Yeah, I think any neural network that guesses the next word or something like that, it works pretty well. And Benjamin says, could you play with different layers? Yeah, I think you can, but if they're seeing that the last one works. The number Kanishka, sorry, says the number of dimensions is embedding equal to the number of neurons in the second last layer of the NN. Exactly. Yes, totally. You nailed it. The number of dimensions in the embedding is equal to the size of the last layer. Okay. So that's how we created these embeddings. There's other ways. Okay. Does increasing the size works better? Too huge, that not I don't know if that makes such a big difference, but big embeddings work well, so if you have hundreds or thousands, work well. For different applications, you want different embeddings. Search, for example, you have a few hundred, and for transformers, different sizes, but you kind of play with it. It's more like playing with this. By the way, sometimes I miss questions. Feel free to ask it again if I miss it. Sometimes it just kind of goes off the window, so feel free to ask it again. But anyway, so that's, I hope I made a big enough deal of embeddings. They are the most important thing in this thing, in this natural, in large language models. And so what happens is that you turn every word into its vector, and then you have a bunch of vectors. Okay, so we've gone through here, and don't worry, I'm gonna go faster with the other ones. We're not gonna stay here all night going with this architecture. But I'm going to go with positional encoding, which is not that long and not that crucial, but it does something. I'm going to do positional encoding, and then I'll look at questions. Okay. So positional encoding takes care of this kind of thing. If I say I'm not sad, I'm happy, or I'm not happy, I'm sad, it's the same words, it's the same vectors, but it means the complete opposite. So what do? It's kind of hacky. What would they do? But what they do is they add a different thing to the first word, to the second word, to the third word, to the fourth word. And in that way, you get sort of modify the vectors, and you're adding some like e to the something or sign of something, some values that are sequential. And then you just kind of modify them in a slightly rough way. But for some reason, the neural network picks that up well. So this is slightly hacky, but it works. Fact is, you just add a different thing to the first, second, third words, and then you get positional encoding. Let's stop for questions. Google used 4096 the size of embedding vector, correct? How are we measuring that the output embeddings are the best? Similar words being closer. That's a great question, Anusha. Yeah, I don't know. I think good embeddings tend to have good, like you can use the embedding for training models like classification, etc., and see how well they do. As far as I know, that's the best way to, it's more of an indirect things to check embeddings. I don't know if there's any concrete metrics for checking in embeddings. Hakan says, but different sequence of words prior the word we want to work with will create different embedding. How can we handle that? You mean in the neural network? I'm not sure if I understand the question. Different sequences of words prior to the word we want to work with will create different embedding. How can we handle that? No, not in this neural network. This neural network doesn't handle sequentiality. It just throws in like a bag of words. So not for this one. Other more complicated neural networks may, but not this one. Okay, I'm gonna go ahead and then I'll answer questions in a few minutes. So the next big thing that happens after positional encoding, you have a bunch of vectors, and now it's the neural network stuff that's happening. So the neural network that we built before to guess the next word is what happens here in the blue, except for the attention mechanism. Attention is a big deal. Attention is what I think would make these models go one step further. Okay, and what attention does is the problem we had at the beginning with the apple that we didn't know if it was a fruit or the brand. Well, the same thing happens. That's what attention takes care of. So, for example, if I have the sentence "the bank of the river" and I have the sentence "money in the bank," I'm talking about a different bank, right? Bank here is that little piece of land around the river, and this one is the institution with money. And the question is, how would the computer know which bank I'm talking about? So who can help me out? Who can give me an idea of why? What on earth would the computer know? Banking on you. Nice. In the meantime, I'm going to answer a question here. Clint says, what was the key to determine that neural networks work well for some of these tasks? Ability to use sufficient training data and sufficiently beat neural networks? Yeah, I think the fact that it's good on the applications is what determines if neural networks work well, how well they do for tasks. Context, Shri says context. Yes, she says context as well. Yes, absolutely, context. Engrams may work, but I think we're gonna go with context, which is related to an engram, is actually the words around it, right? Multi-head attention using engrams approach. Yep, multi-head attention is actually what we're gonna get. Position in the sentences build. Yep. The idea is that what tells me in the first sentence what bank I'm talking about? The river, right? That's the key word there. River tells me that I'm talking about the bank of the river. And here the word money tells me that I'm talking about the bank of money. So it's really using the other words. I'm going to piggyback on the neighboring words to be able to tell what bank am I talking about. So what I'm going to do, I like to imagine this like gravitation. I like the words kind of gravitating towards each other. So the word bank and river gravitate. And how do words gravitate? Like the word planets gravitate, right? Like if I have, for example, the Earth, it gets pulled by the moon because the moon is close, but it doesn't get pulled by faraway planets because they're very far away. So words that are close pull each other, and words that are far don't pull each other. So for example, in my sentence, money in the bank, the words bank and money are close. So let's say the word bank gets pulled by money, and I'm only doing it the word bank, but you can do this in all the words. The word bank gets pulled by the word money, and it doesn't really get pulled by the words in and there because they're in Jupiter, okay? So if I were to make the words gravitate, then bank gets closer to money and money gets closer to bank. And so that's what we're gonna do here. I have, if my embedding is good, then on one side of the embedding, I have all the financial words. And on the other side of the embedding, I have all the words of the nature. And then if I want to use the word, the sentence money in the bank, then the word, I let my word bank gravitate towards the word money. And so now I have a new word bank that is somewhere here. Remember that the embedding is coordinates, right? So I've changed the coordinates of bank. And now I have this red bank that's closer to money. And that one is a better bank to use than the original bank. And now when I use the bank of the river, then I gravitate the word bank towards river. And now I have a new word bank. And that's the word bank that I'm going to use. The green bank is the one I'm going to use in the bank of the river. So this is what attention does, right? Attention takes the word in the sentence and gravitates them toward each other. And so eventually they're a better word, because now my word bank is better when I gravitate it towards money or towards river, depending on the sentence, right? So that's what attention does. So it takes, for example, money in the bank. It doesn't know what bank you're talking about, to knowing what bank you're talking about. People are talking about multi-headed attention. What is that? What multi-headed attention, what it does is it just takes different embeddings. So I have a bunch of, I take my original embedding and I modify it in different random ways. I apply attention in all of them and I combine the results. That's multi-headed attention. Okay. Jack says, what type of attention are you using? I'm using self-attention here. Self-attention, but if I use it on several different embeddings, I use multi-head attention. Each one is a head. Okay. Do let me know if anything's not clear, and I'll repeat it, but that's the key step. As I said, that's a step that made transformers go one step further. Attention. And I think that's pretty much it, right? Because the feed forward is what we already saw. Abby says, can you explain that last slide? You mean this one or the next one? This one. Okay. The idea of attention is that it moves the words around. So if I have the word bank and I don't know what bank to use, what I do is I gravitate it towards the words in the sentence. And so as you can see, the red bank is a better bank to use in the sentence money in the bank than the black bank, right? And the green bank is a better bank to use in the sentence the bank of the river, because that green bank is closer to the nature words and the red bank is closer to the financial words. I'm talking about the coordinates, right? Because the coordinates are the numbers that I'm going to turn the word bank into, right? Like says, are embeddings always metrics of similarity, or do we appear in the embedding to mediate the distance? We never use distance, we use similarity. Okay, so similarity is a high number if the words are close and low if they're far, as opposed to distance, right? Yeah, Sid, that's a great question. How are exceptions handled? Maybe there is a bank by the river. So this is a terrible example in that sense. There could be an institution, a bank close to the river. The idea is that you want to use a longer context, right? So I wouldn't use that sentence, but I would use the entire paragraph. And hopefully, if I'm talking about the bank, Wells Fargo, that's really close to the river, it's still like I would still catch the fact that I'm talking about institution from the general paragraph. So maybe somewhere else in the paragraph, there's the word money, there's the word deposit or something. So I would just expand my window and have a much bigger window of text. And yeah, Fernando says riverbank and trust. That would just mess up the model. That's the bank is near the river. Yeah. So ambiguities appear, but the fact is, you know, the bigger you take your window of text, the hopefully the less ambiguity will happen. And if they happen, they happen. You know, just try to minimize the amount of times they happen. All right. How are we doing here? Sorry, I keep losing my cursor. 1 second. Okay, so feed forward. So the feed forward is what we already saw. The feed forward is this part, this neural network that guesses the next word. So if you had this as the neural network, right? These are the feed forwards. And all we do is add attention in between. So we take a big neural network that guesses the next word, and you add attention layers in between and train it like that. So that's how it looks. This part's a little abstract, but bear with me. You just imagine combining a neural network with attention in between and having several layers. Here I have 3, but you can have 10 or 20, as many as you want. And that's the idea. That's the series of transformer blocks. That's the neural network part of the transformer. And finally, there's something called the softmax, which simply just takes the transformer outputs a bunch of numbers, and the softmax just takes them and turns them into probabilities. Why do we want probabilities instead of scores? Because I don't want the transformer to always be giving me the same answer, right? If I ask it, I want it to give me different answers. And so what I do is softmax, if you've seen it, it's a formula with ease and stuff. If you haven't seen it, don't worry. Something that turns things into probabilities, into numbers that add to 1. And then I just sample out its probability. So I instead of picking the word once always, which is the biggest score, I just pick once with probability 0.5 and in with probability 0.2 and there with probability 0.3. And most likely I'll end up with a good word, because good words have higher probabilities than words that don't fit. So that's pretty much the architecture of a transformer. Let me just recap. Tokenization turns words into numbers. Positional encoding gives the words order. Attention gives the words context. So bank of the river, money in the bank. And the feed forward is the one that guesses the next word. And the softmax is the one that assigns probabilities. So this is a transformer model. Quick question, Amir and Babar, how are we doing with time?
I think we are good, Luis. We want to keep about 10-15 minutes for quick Q&A towards the end. But you know, maybe in the next 5 minutes we can start wrapping up and see if there are any other questions.
Okay, I'm pretty much done. I can ask for one. I can say one more thing, which is post-training, because here's the thing. So the transformer architecture, beautiful, blah blah, researching, but you put this thing and it doesn't work. Why does it doesn't work? Because the data is horrible. These things are trained on the internet. The internet is not a repository of brilliant information. Is not a question answering. Is not formed in question answer. It's not. It's a bunch of stuff where everything happens, right? So you need to fine tune things. So I'll give you an example. If I tell a transformer model to write me a story, the transformer model doesn't know I'm asking it to write a story. It just tries to see what the internet would say right after the words write a story. And as I said, the internet is not a repository of questions and answers. The internet many times has things like this. You have an entire list of questions. It could be an exam. The first question is write a story. The second is write a poem. The third is write an essay. So transformers, if you tell them, write me a story, they answer, write a poem. Or if you tell them, what's the capital of Texas, it asks, what's the capital of Oklahoma? It's, you know, not gonna say Austin, right? So what you do is you post-train them. So after you train them on the entire internet and they know how to talk, then you post-train them on the task that you need. So you add them on extra training data on sets of commands and responses, right? So questions and the responses. or commands and what they're supposed to do. So write me a poem followed by a poem and a question followed by the answer. And then they learn that they're supposed to do that instead of just continue the sentence based on what the internet tells them. And here's another problem. Let's say chatbots, right? Like I ask it, who was the first person to win 2 Nobel Prizes? And it goes, Marie Curie. And then I continue talking to it. Ah, cool. Yeah, whatever. And then I say, where was she from? And it has no idea what I'm talking about because it can't pick up the fact that I'm talking about Marie Curie, right? So what do you solve? How do you solve this problem? How do you give them a little bit of memory? You just train it on huge chats. You put it a lot of chats and train it there until it starts optimizing and realizing that the best that it's supposed to learn things from before. So in particular, if I have a chatbot, I can turn it into a specialized chatbot by post-training it on specialized data. So if you work at any particular company, bank or something, you just put the data from there and it answers questions from there. So the post-training is a huge thing. And that's really what fine-tunes it to work really well. It's really all of that. That's pretty much all I have. So let me give you some links and stuff. Here's some, if you're interested in seeing more of that, this is the Discord community at Cohere. And I'm going to show you the dashboard in a minute. There's a QR code. As I told you before, check out LLM University, launched today, brand new. You're the first people to hear about it. So check it out, LLM University. And I will add some links. Yeah, and then I think Babar and Amir can help me with the links later, right? Here's the Cohere Playground, which I'll show you in a minute. Link is llm.university. Okay, llm.university. And here are some of my coordinates, which Babar talked at the beginning. There's the YouTube channel. If you enjoyed this talk, there's a lot more there on all of machine learning, the neural networks, etc. So check it out, serrano.academy, or the page, or the you can tweet at me if you want. Luis likes math, and Babar will share the discount code for the machine learning book. That also has everything explained in this sort of simple terms. And I think just to wrap up, let me show you the playground. So you go to dashboard.cohere.ai and yes. Questions? I heard somebody talk. I'm not sure you have questions. Check out this, play with this. Scott, generate, classify, embed, and summarize. So I can ask, for example, here are some examples, turn the following for the future into a list of benefits, blah, blah, blah. You make it run and it just does what you're used to see in ChatGPT, basically. Classify is actually pretty cool because classification is an old thing. It's from 10, 15 years ago. So it's nothing new, but with a good embedding, remember I made a big deal about embeddings? With a very good embedding, you can train a classifier on very, very, very few examples. So here I have, for example, a banking, a data set of questions people ask in the bank. And I have a bunch of possible, savings account indexes, taxes, and just with 4 or 5 examples, even just 2 or 3, it trains a good classifier. So it actually tells me, what these questions may be. Then there's embed, which is the one I was showing in the examples. I can give it a bunch of titles of things, and I can say embed, and this one only shows 2 coordinates, but if you use the one with the code, you can get an API and actually run it in your code. You get to play with the big ones, the embeddings that are big, and obviously, as you can see, similar sentences get sent to similar points. And here's about banking. This one's about Bitcoin. Here, I just random stuff. And then there's a summarized one, so you can actually just pick a random page and summarize it. Here I picked a random one about a hackathon, and it'll summarize it. You can have a bunch of parameters. You can say long, short. You can make it in paragraph mode or in bullet mode. Anyway, play around. dashboard.cohere.ai. And I think that's pretty much my talk. So I'm happy to answer any questions. And thank you so much for your attention.
Luis, thank you so much. This was great.
Great. Thank you, Luis, and thank you, Babar, for arranging very exciting talk. Usually, Luis, we moderate, but you have been an amazing speaker with wonderful content and also multitasking, taking all the questions yourself, right, and not relying on me or Babar. So you're making us fire ourselves.
Thank you. I even asked my own questions and the crowd was very good at answering them. So I was impressed.
Folks, one thing before I put the questions, I also got some direct messages on people who got dropped and they joined again and were asking for recording. As always, we'll put the recording in the Dallas AI discussion group. Barbara will also post all the URLs as well as the discount codes. I'm going to put those again in here, the 3 channels for Dallas AI. All the event content goes in the first one, the Dallas AI LinkedIn group. As always, you are encouraged to join all 3. That's the best way to engage with us. I guess I'll leave 10 minutes for additional questions, folks.
Yeah, any questions, feel free. I have, maybe I'll just call names since I see a Storm. How about?
Hey guys, so I've got a question, and I don't. First off, let me start by saying I'm really new to this whole topic, and I really don't know what I don't know. But I wanted to talk a little bit about the idea. I'm getting into, playing around with natural language processing in general. So this has been very enlightening, and I thank you, Luis, and everybody for putting this on. It's been really great. But I wonder if you could talk a little bit about the idea of matching name value pairs in text. Let's say I had text and I had some keywords that I wanted to find, and I don't know, as a rough example, let's say I had a lease and I knew that I wanted to find the monthly rent and I wanted to find the lessor and the owner, and I wanted to search for that, but I knew certain terms I wanted to find. But how do you go about doing that in an AI way in general? And I realize that's a big topic, but I wonder if you could talk about that for just a bit.
Entity extraction. So you're talking about entity extraction, right? Like you can get a receipt, for example, and it tells you what the price is, what this, you can get the taxes, right, and it tells you like that. That is actually with a transformer, like you can train it on that. So really, the transformer is done, all that it does is you have to teach it, right? So for example, if you have a big data set of what you want, so you have a lot of data set of documents and the entities you want to get out, or receipts with the price, if you train it with that, then it learns to mimic that. So as long as you have a big data set of what you want, the transformer will learn that.
Okay,
right?
That's pretty much what I. That's pretty much what I thought. But I'm at the level of I'm trying to use Spacey to do basic pattern matching and look for certain patterns and stuff. And I'm realizing that this is a much more difficult problem than I
You know what, a few years ago, we tried to come up with an algorithm for that, but now all you do is take the data of the examples that you want to give the computer and just feed them to a transformer and let it do its magic. And for summarization, that's how it works. For entity extraction, for translation, for anything, if you just give it the data set of what you want, it mimics it. They're that powerful.
Thank you.
Great question.
I
want to call on
2 hands on Joydeep and Storm. They have been waiting patiently.
Yes,
let's have good sequence, right? You want to start, Joydeep? You want to ask your question or post in the chat?
No, let's go with Storm because I think Luis called his name first. So Storm.
Okay, let's have Storm and then Joydeep. Thank you.
I don't mind waiting, but thank you. I appreciate that. So just a little context too. I have worked in healthcare my whole career. I'm a registered nurse and also now product and health IT for the last 20 years. But most of that time has actually been spent with nuance and natural language processing. So, and now with Microsoft taking over, kind of buying nuance and now their investment in OpenAI. So they're actually integrating those applications. My question is previous to GPT-4,
Yes.
we would utilize, or the thought process was very kind of a pyramid. So in the manner in which we thought about this, learning from an individual user, a user would have an individual profile, which would, the more that they used Dragon, the better it got at understanding that individual user. That said, that also, that user was divided into a geographic location, an accent, a medical specialty. So then that information not only now improved their voice recognition, but it's now put into a pool and now filtered out into all of these other silos, which ultimately could be cross-referenced and then made, you know, local geographies, for instance, that might have very different nomenclature than others, different specialties, different accents, and even different parts of the world that they would talk differently. So my question is, speaking to GPT, for instance, where we're talking about a static, like right now, it's just a copy from months ago, and it's not pulling in any of that real-time data, at least not currently. But am I understanding that correctly? Like that's the future state that we would imagine this would be learning real time, not only to improve my individual experience, but the experience overarching.
Absolutely. These things need to be trained in real time. I think ChatGPT has a thing that is until 2011, I believe. BARD maybe more often, but these models are need to be trained all the time. The one that we have is called, the latest one is called Command Extra Large Nightly. Nightly means, in theory, train every night, but it's just a word for saying often. It's every week. So every week it gets retrained with new data and with the conversations that people give and the answers that people give, thumbs up, thumbs down. But yeah, these models need to be basically, they don't get trained in real time with every input, because that'd be too expensive, but they get trained in batch, you know, every so often. But they do need to be upgraded all the time. Yeah.
So an SFTP for voice recognition. Never mind. NLP. Never mind. I'm just okay. Cool. I just was thinking about the future state. I know that we're not there yet. We're in infancy.
Yeah, I think in everything we're in infancy, but you know, we're moving. And then voice recognition is doing quite well. I mean, I think it's more about the data really, right? Like if we need to get, like, you know, diverse data, different accents, different things. And if that sometimes is the more challenging part than the actual model. But combining recognition and this sort of text processing, it gets pretty, you know, things get pretty advanced. So I wouldn't be surprised if there's, you know, big advances in the next short amount of time. Thank you. Good question. So we had Joydeep and then maybe Istiak, or feel free to, Amr, feel free to call anyone if you have more.
Yeah,
You can go.
I can go.
Joydeep, you want to go ahead?
Okay,
Yes, I can go.
Yes.
Before I start, thank you, Luis. It's an honor. I've gone through all your YouTube videos. I have dropping machine learning, and it's just an honor to see you. The way you explained it out of this world, and some of you have experienced it today. So my question is a quick question, but a little bit of a solutioning piece on the fine tuning. So I have these PDFs, which are all our contents that we send it to our different customer, and the contents can be all different types of content, and it has disclaimer at the end. Now, what I'm trying to do is, you know, build a model using fine tuning and auto generate those disclaimer. Now, we are using GPT-3, and the fine tuning is pretty much the prompt and the ground truth. I'm not able to correlate what should I feed into the model, or shall I use a different technique like, you know, transfer learning to solve this problem?
Ooh, sorry.
Whether Cohere has anything that we can.
Yeah, maybe. Sorry, can you repeat the problem? There you have what's the input and what's the output?
So the input are content.
Content.
Communication that goes out. The output of that would be all the disclaimers that should be attached to that content. So it's the the GPT model or generative AI models to generate the disclaimer from the content. But these are all
Okay, I get it. So you have a content, you have yeah, like some text of something, and a human would write disclaimers on that, and so you generate the disclaimer. Yeah,
Yeah, and
definitely a transformer. Definitely, what you want to do is have a bunch of data where you have the input is the content, the
Mhm.
output is the disclaimer, and you can train a transformer for that. And that's called a few shot learning. So you just try a few, have as many of them as you can, and post train your transformer. It could be the Cohere one, the ChatGPT one, or anything like that,
Mhm.
and post train it with that. But you already have, the key is the data. The data is disclaimer, sorry, text with its disclaimer. That's the thing I would do.
Another challenge is the text can have multiple disclaimers. So you can imagine the different flavor of that content gets added with multiple disclaimers, so that the generation model should be able to generate multiple disclaimer, and that's where the challenge is. It's not one-to-one with the content.
Yeah, well, would you want it to generate all of them or just one?
No, all of them which are
Yeah, then
pertinent.
whatever you want the transformer to do is what you give it in the data, right? So if you have a
Okay.
data set of like text and the 5 disclaimers, and then this text with 14 disclaimers, and this text with 1 disclaimer, you just give it that.
Okay.
Yeah, give it the way a transformer is just a person who the parrot just mimics whatever you give it. So give it that.
Okay, I'll try.
And then that, I think it should work. Yeah.
Great. We'll take a last one, folks. Ishtiaq?
Yeah.
Hey, can you hear me?
Yeah,
Yes,
we can
I can hear you.
Hey, I'm Ishtiaq Mahmood. I work in the university, actually medical side of the university with the researcher. I'm new to the transformers technology, trying to learn it. I'm familiar with the NLP in the past.
Yes.
Again, I have a computer science background. I just play with things whenever I find it interesting on my own. So again, lately I'm getting familiar with the ChatGPT.
Yes.
And ChatGPT, from my understanding, is trained with what, a 1.5 billion parameters.
Something
So
like
it has knowledge. But then I'm trying to put it in a problem, a simple problem, and try to see how it's going to solve it. So a simple problem is, in that way I can understand it. So simple problem is that I want to train it so that I can use the run book when there's a problem. I can find the right run book. Now, biggest problem I see is that if I want all my run book content and to be fine-tuned with the ChatGPT, to me is like a boiling ocean with data. That a lot of the data may not be related to my run book data that I have. So then I was thinking that whether should I create something from scratch, train model, and just use my data and train it with that data, something smaller, and that would gonna be good enough for me.
Okay, first of all, what's a runbook?
Runbook is in a help desk. Whenever there's a issue, the help desk is given a list of tasks that they can do to resolve that problem,
Okay.
and they have a lot of them.
I have a suggestion for you. I mean,
okay.
I think if you can get it, I'm not exactly sure what the exact problem is, but if you can get a transformer, if the first thing to do is try what I've been saying, right? Try to train a transformer with the right data. Try to see the data you want to mimic. But if you want to go more, if you really want to get into the details of it, then don't train something from scratch, but train it from the embedding. So let me, what I mean is by this, I would never train anything from scratch anymore, because that's like reinventing the wheel, right?
Gotcha.
But if you want to go the most bare bones you can, the most basic you can, then use a powerful embedding. Oh, did something happen here? Am I not sharing anymore?
No, we're hearing you.
Great. Sorry, I just the screen moved. So what you do is at least use the embedding. That's, to me, that's the most basic you can get, because embeddings are very good. And if you start training something from scratch, you lose that embedding, and all of a sudden you're starting from zero, and you need millions of data points to train something well. Whereas with an embedding, you know, the computer already knows what's happening, right? So what I would say is, as long as you take your text and put it through a good embedding, used with a transformer, like use, for example, the one I showed you in the dashboard, or something that's pretty solid, and then train your models from there using any methods that you know from before, a neural network, or classifier, or clustering, or anything you want, but start with the embedding, basically.
Yeah, just one follow-up question regarding that. So if I have multiple of this trained model, and they are trained with a specific data like cancer or something like that, but they have local individual knowledge about that, how could I use all this different knowledge base with a single like more like a chatbot to ask question and get answer? It's like a multiple people has different knowledge, and I'm asking to solve a problem with all this knowledge.
You have a bunch of models that have different knowledge.
Correct. It's like somebody knows how to cook rice, somebody knows how to cook curry. I say make a biryani as an example.
Well, that'd be good.
Yeah, so
I'll jump in. Maybe feel free to connect with Luis over LinkedIn, and maybe add some details, and he'll be happy to answer.
Yeah, let me put in my LinkedIn here, actually. So yeah, I gotta think a little bit about that one. So yeah, feel free to send me a message. Let me put my LinkedIn here. Let me just give it to you, and feel free to add me there.
While you're doing that, I didn't see all of the slides that you showed with all of the different contacts and things and discount code and whatnot. None of those, of course, were clickable. And I did get the things for the Dallas AI, but nothing for you. I mean, I can look you up on YouTube, or I mean in YouTube and LinkedIn, if that's where I can get those things as well.
Let me just bring some things here.
Luis will be sharing all the links with Babar, and Babar will be posting it in the Dallas AI group. Again, these are 3 channels, and the first one, Babar will have it posted, all the links that Luis had in his presentation, plus the recording of this talk. So if you have things that missed,
that's right. That's right.
I'm putting them there in the chat if you want to copy paste in the meantime.
Thank you.
Yeah, and Luis, such a great session, right? Amazing.
Thank you so much. Thank you. I had fun. You guys answered all my questions, so it's always nice.
Thank you again, Luis. Thanks, Babar, for arranging, and thanks to the audience for great questions.
Great audience.
Great night. Bye-bye.
Thank you. Bye-bye.
Bye-bye.